It's time for our hands-on session to implement a panel regression in Stata. In our previous primer, we already learned that our panel data has a specific format, namely that we observe a unit, like a firm, or in our case, an ice cream parlor, over time. And each unit and time combination is unique in my data set. Now, let's check out how this works in Stata. I open my multivariate statistics do file, and as before, load my ice cream data into Stata. Just as a quick recap, our data has different locations for ice cream parlors, the park, city center, and the train station. And each of these locations are observed over time. So I have my purchase date here, and each purchase date is unique for each ice cream location. So for example, November 7th, 2019 only appears one for the park, the city center, and the train station. I now need to tell Stata that my data is in that particular panel format. And I can do this using the xtset command. So let's scroll down in our do file to the bottom where I find my multivariate statistics part on panel regressions. Now, the xtset command is the command that we need first. It defines the panel variable, which in our case is the location where my ice cream parlors are, and a unique timestamp. So these two variables have to be set in a numerical format. A string format doesn't work, but we already created those in our data preparation, so we're all set to go. And Stata now confirms that we now have the panel variable location numerical and the time variable timestamp. Now, when running a regression using panel models, we can do that using the xt prefix to any regression command. For example, xtregress will turn the cross-sectional panel or the cross-sectional data that we had previously into a panel regression model. And the rest of the command is very similar. We have our dependent variable, our independent variables, and control variables. As you will notice here, we have a fixed effects model specified by the FE option. There are basically two models, especially when running a linear regression model, a fixed effects model and a random effects model. And they are a little different. So for a fixed effects model, imagine you own a chain of ice cream parlors in various locations, and you're interested in understanding how the outside temperature affects ice cream sales in these different spots. A fixed effects model would look at each parlor individually, considering that each location might have a unique factor or several factors influencing sales, like local preferences or competition. On the other hand, a random effects model would treat the parlors as a random sample from a potentially larger universe of ice cream parlors. It assumes that while each parlor might be different, they are not so unique that you can generalize findings across them. Of course, the question now arises which model I should choose, but we'll come to that in a second. Let's first look at some of the outputs. In this case, I find that the temperature and child variables are, again, statistically significant given the low p-value, and I see that income is not significant given a relatively high p-value. And another thing that strikes me is that the location and train station were omitted from my output. And this is because when you're running a fixed effects model, you're only looking at the variance across time within a unit. Everything that is time invariant will automatically be dropped. Another example would be if you're running a firm panel regression and observing a firm every year, a variable like industry that is constant over time, unless a firm switches industries, would be omitted from the output. That is an important consideration also in choosing between a random and a fixed effects model if you're interested in estimating these time invariant effects. After my regression command, I store the results in Stata's memory with the estimate stored fixed command. We will come back to those later when we implement our Hausman test. And now I want to compare that to the random effects model. The only thing that changes here is the random effects model. Now you see that the location and train station are included in my regression. Of course, it is debatable whether these make logical sense because they are also part of my panel variable, so probably it doesn't make sense to control for them at this point. But nonetheless, you see that a random effects differs in comparison to the fixed effects model when including time invariant variables into your model. Now let's come to the Hausman test. Here is the command. The Hausman is a standard command in Stata that tests for the differences between a random and fixed effects model. So the Hausman test here would help you decide which model to use by testing if the unique characteristics of each ice cream parlor, like its location or size, that are not included in the model are correlated with the predictor variable, the temperature in this case. If they are correlated, the fixed effects model is more appropriate because it controls for these unobserved characteristics. If not, the random effects model could be better since it's more efficient and still provides consistent estimates. An important variable to look at is the p-value that relates to the null hypothesis. The null hypothesis in this case is the difference in coefficients is not systematic. If you have a low p-value, let's say 0.001, this would indicate that a fixed effects model is better. And if you have a high p-value, in our case it is 1 or close to 1, it suggests that the differences in coefficients between the fixed effects and the random effects model are not systematic. In the context of our ice cream parlors, this means that the unobserved unique characteristics of each parlor do not significantly impact how temperature relates to ice cream sales. Therefore, you might lean towards using a random effects model, assuming it's more efficient and the unobserved factors are not biasing your results. There's also another theoretical choice you need to make. If you use a fixed effects model, you're observing the variance within a unit over time. And it is harder then to compare across units. So sometimes you may be, for a theoretical reason, interested in comparing units with each other at a certain point in time. For example, you may be interested in how firm strategies in a certain year differ. And then a random effect model might be more appropriate for you for that very theoretical reason. Thank you for tuning in to Statistics Made Easy and this panel session. I look forward to seeing you in our next session.